In this video, we're going to define some mathematical statements. And some statements are true by definition. So, for example, if we define a cyclic quadrilateral is a quadrilateral where all four vertices lie in a circle, it follows that a circle can be drawn through the four vertices of a cyclic quadrilateral. So I'm just going to remind you of some symbols that we've previously been introduced to. The symbol of implication, which means it implies, so it's like a sort of double arrow to the right. So if P then Q, we write as, P implies Q. The symbol of equivalence is saying that if P implies Q and Q implies P, then P and Q are equivalent. And our third symbol is to represent negation, which is that idea of not, which is most commonly when we're using proofs, we use this symbol. We've seen some other symbols that we can use to represent not P, as we have seen with our probability. So we're going to have a look at what we mean by the converse of a statement. So the converse of a statement is where we flip around the two parts of our statement. So if we say if P then Q, and we know that as, if P implies Q, the converse will be Q implies P. So we've simply just flipped around the P and the Q, the parts of the statement. Now, just because the initial statement is true, it doesn't mean that the converse is also true. Okay, so just because P implies Q, which was our original initial statement, it does not automatically imply that Q implies P. So let's have a look at a couple of examples. So if we say if x equals 2, then x squared equals 4, this statement is true. But if we do the converse, if x squared equals 4, then x equals 2, this statement is actually false because x can also equal -2, not just equaling 2. Let's have a look at another example. In our second example about the converse is if a triangle has two equal sides, then it has two equal angles. So the converse is just swapping around the equal sides and the equal angles. So if a triangle has two equal angles, then it has two equal sides. Now in this case, we know that this converse statement is in fact true in this case, but it's not always automatically going to be that way. Okay, so we can actually, because the initial statement and the converse are both true, we can define this using equivalence. Because we said in a triangle, when we've got two equal angles, this implied in the triangle we have two equal sides. And we know that we can flip this around, so we can use that equivalent sign. Okay. One other thing to note about the idea of this equivalence of P being equivalent to Q is that we can often hear the saying P if and only if Q. And this actually gets simplified to P if and only if Q. So if you see a statement like that, they're talking about equivalence. Now we're going to consider the inverse of a statement. So we've got the statement if P then Q. So we know that this is if P implies Q. The inverse is the negation of them both. If not P, then not Q. So if not P, then not Q. Again, with the inverse of a statement, just because the initial statement is true, it doesn't mean that the inverse is also true. It doesn't automatically imply that it's true. Let's go back to our first example we had earlier. It said if x equals 2, then x squared equals 4. So the inverse would be if x does not equal 2, then x squared does not equal 4. Well, we know, in fact, that this is false because when x equals negative 2, x squared can still equal 4. So what we've actually got here, by saying actually no, this is false, because when x is negative 2, x squared is 4, is what we have previously talked about, which is a counterexample. And as soon as we have a counterexample, we can prove that a statement is in fact false. So in our case, the initial statement was true, however, the inverse statement is false. The third type of statement we're going to have a look at is called the contrapositive of a statement. So if we're implying that P implies Q, so if P, then Q, the contrapositive, which is an interesting word, is if not Q, then not P. It's like having the converse and the inverse wrapped in together. So what this is saying is if not Q, then this implies not P. What is really important to note about the contrapositive is the contrapositive is also a true statement. And this is very handy when we're trying to complete a proof, because sometimes it might be hard to prove the initial statement, but perhaps we can turn it around and prove the contrapositive. So let's go back to our example that we had. If x squared equals 2, then x squared equals 4. We know that this is a true statement. So the contrapositive is going to be turning that around. So there's our P in our Q. So now we're going to say if x squared does not equal 4, so not Q, then this implies that x does not equal 2. So there's our not P. And in fact, this is true. If x squared is not equal to 4, then x cannot be equal to 2. So we definitely know that that contrapositive statement is also true. Let's have a look at our other example about the triangle. If a triangle has 2 equal sides, then it has 2 equal angles. And we know this initial statement is true. Let's turn it around. If a triangle does not have 2 equal angles, then it does not have 2 equal sides. And we know that is also true. So as a bit of a summary, if we take our initial statement of if P, then Q, and we know that we can represent that with symbols of P implies Q, then the converse is swapping around the Q and P. If Q, then P, or Q implies P. We know that if the converse is true, then we have equivalence between them, but only when the converse is true. But we know that, I'll highlight in yellow, that the converse and the inverse are not automatically true. So the inverse is the negation of P implies the negation of Q. Not P, then not Q. And the contrapositive is not Q implies not P. And we know that this is always true. So let's take a look at some questions. In our first table here, we have a statement and we need to identify the converse and the contrapositive. So if 2 angles are congruent, then they have the same measure. And we know that that is true. So the converse is going to be swapping around if they are congruent, they have the same measure. So we're going to swap that. So if 2 angles have the same measure, then they are congruent. The inverse is the negation. So if 2 angles are not congruent, then they do not have the same measure. And the contrapositive will be if 2 angles do not have the same measure, then they are not congruent. Perhaps you'd like to pause the video now and have a go at part B, seeing if you can fill in what the initial statement was, that is in fact has to be true, and what the inverse will be. Okay, so we've got the converse. If a quadrilateral has two pairs of parallel sides, then it is a rectangle. Well, we know that that's not the case because it could be a square, it could be a rhombus, it could be a parallelogram. So the initial statement would be the flip of that. So it must have been if a quadrilateral, I'm just going to simplify this, is a rectangle, then it has two pairs of parallel sides. And we need to check that this statement we've got is true. If a quadrilateral is a rectangle, then it has two pairs of parallel sides. Yes, it's true. So the inverse of that would be the negation. So if a quadrilateral is not a rectangle, then it does not have two pairs of parallel sides. And the contrapositive would be if a quadrilateral does not have two pairs of parallel sides, then it is not a rectangle. That's very true as well. Okay, let's have a look at question 2. Let's assume the following statement is true. Let's write the converse of the statement and then state whether the converse is true or false and write equivalence or not equivalent. So if a polygon has exactly 3 sides, so there's my event P, then the polygon is a triangle Q. So we're going to assume that's true. So let's do the converse, which is going to be flipping the P and the Q. So if a polygon is a triangle, so there's Q, then it has exactly 3 sides. A polygon is a triangle, then it has exactly 3 sides. Well, we know that it's in fact true, so we have an equivalence. For question 3, for the following statement, state whether the initial statement is true or false. Write the inverse and state whether the inverse is then true or false. So our statement is, if a positive integer has exactly 2 factors, then it is prime. Well, I say the initial statement is true. Let's write the inverse. I'm just going to write the inverse here. So the inverse is the negation. So if a positive integer does not have exactly 2 factors, then it is not a prime. And if it doesn't have 2 factors, it's not a prime. This also is true. So the inverse statement is also true. In our last example, we've got assume the following statement is true, and we're going to write the contrapositive of each statement and then check the contrapositive is true because it must be true. So if a triangle is scalene, then it has 3 different lengths. So the contrapositive, if a triangle does not, because it has to be the negation, have 3 different lengths. So remember, we're going to do the negation of the Q, and our P can be the scalene, and the lengths of the sides, then it is not scalene. So if it doesn't have 3 different lengths, maybe 2 of them are the same, maybe 3 of them are the same, so it's definitely not scalene. It is in fact true. So now it's your turn to have a go at our question 5. So for each of the following statements, write the converse, inverse and contrapositive statements, and in each case state whether they are true or false. I'd like to pause the video and then you can come and have a look at the solutions.